In physical chemistry, thermodynamics, chemistry and condensed matter physics, a critical point, also known as a critical state, occurs under conditions at which no phase boundaries exist. There are multiple types of critical points, including vapor-liquid critical points and liquid-liquid critical points. Pure substances, vapor-liquid critical point. The term critical point is sometimes used to specifically denote the vapor-liquid critical point of a material, above which distinct liquid and gas phases do not exist. As shown in the phase diagram to the right, this is the point at which the phase boundary between liquid and gas terminates. In water, the critical point occurs at around 647 K and 22.064 A. As the substance approaches critical temperature, the properties of its gas and liquid phases converge, resulting in only one phase at the critical point, a homogeneous supercritical fluid. The heat of vaporization is zero at and beyond this critical point, and so no distinction exists between the two phases. On the PT diagram, the point at which critical temperature and critical pressure meet is called the critical point of the substance. Above the critical temperature, a liquid cannot be formed by an increase in pressure, even though a solid may be formed under sufficient pressure. The critical pressure is the vapor pressure at the critical temperature. The critical molar volume is the volume of 1 mole of material at the critical temperature and pressure. Critical properties vary from material to material, and for many pure substances are readily available in the literature. Nonetheless, obtaining critical properties for mixtures is more challenging. Mathematical definition. For pure substances, there is an inflection point in the critical isotherm on a PV diagram. This means that at the critical point, that is, the first and second partial derivatives of the pressure P with respect to the volume V are both zero, with the partial derivatives evaluated at constant temperature T. This relation can be used to evaluate two parameters for an equation of state in terms of the critical properties, such as the parameters A and B in the van der Waals equation, for which sometimes a set of reduced properties is defined in terms of the critical properties, that is, where is the reduced temperature, is the reduced pressure, is the reduced volume, and is the universal gas constant. Principle of corresponding states. Critical variables are useful for writing a varied equation of state that applies to all materials, similar to normalization. The principle of corresponding states indicates that substances at equal reduced pressures and temperatures have equal reduced volumes. This relationship is approximately true for many substances, but becomes increasingly inaccurate for large values of PR. Table of liquid-vapor critical temperature and pressure for selected substances. History. The existence of a critical point was first discovered by Charles Cagniard de Lottor in 1822 and named by Thomas Andrews in 1869. He showed that CO2 could be liquefied at 31 degrees Celsius at a pressure of 73 atmospheres, but not at a slightly higher temperature, even under pressures as high as 3,000 atmospheres. Mixtures, liquid critical point. The liquid critical point of a solution, which occurs at the critical solution temperature, occurs at the limit of the two-phase region of the phase diagram. In other words, it is the point at which an infinitesimal change in some thermodynamic variable will lead to separation of the mixture into two distinct liquid phases, as shown in the polymer-solvent phase diagram to the right. Two types of liquid critical points are the upper critical solution temperature, which is the hottest point at which cooling will induce phase separation, and the lower critical solution temperature, LCST, which is the coldest point at which heating will induce phase separation. Mathematical definition. From a theoretical standpoint, the liquid critical point represents the temperature concentration extremum of the spinodal curve. Thus, the liquid critical point in a two-component system must satisfy two conditions, the condition of the spinodal curve, and the extremum condition. In renormalization group theory, the critical point is described by a conformal field theory. According to the renormalization group theory, the defining property of criticality is that the characteristic length scale of the structure of the physical system, also known as the correlation length I3/4, becomes infinite. This can happen along critical lines in phase space. This effect is the cause of the critical opalescence that can be observed as binary fluid mixture approaches its liquid critical point. In systems in equilibrium, the critical point is reached only by precisely tuning a control parameter. However, in some non-equilibrium systems, the critical point is an attractor of the dynamics in a manner that is robust with respect to system parameters, a phenomenon referred to as self-organized criticality. See also. Footnotes. References, revised release on the IAPWS Industrial Formulation 1997 for the thermodynamic properties of water and steam. International Association for the Properties of Water and Steam. August 2007. Retrieved June 9, 2009. External links, critical points for some common solvents. ProSciTech. Archived from the original on January 31, 2008. Critical temperature and pressure. Department of Chemistry. Purdue University. Retrieved December 3, 2006. Hagen Klenet and Verena Schult-Verlind, Critical Properties of I-4 Theories, World Scientific. Paperback ISBN 981-02-4658-7.